Hello everyone. Lesson number 6 is about Newton's laws of motion, and here we start talking about the dynamics part. The dynamics part is concerned with the cause of motion and how objects change its state of motion. The most famous laws of mechanics that are pertinent to motion are Newton's three laws, which are known as the laws of motion. We're going to talk about each law and what it means. There are links for videos that provide you with a better insight into each one of those laws. Those videos are experiments that were done in the International Space Station where the friction factor is negligible. Hence you can see Newton's laws without the interference of external forces. Newton's first law states that objects at rest will remain at rest unless acted upon by an external force, and this is something we are familiar with. In our lives, we see that objects do not move unless a net force is applied on those objects. The second part of Newton's first law states that objects in motion will remain in motion at constant velocity. We learned in lesson number 4 the meaning of constant velocity. Constant velocity means that both the speed and the direction have to be constant. For example, if you have a wagon or a car and you push it, giving it initial speed, let's say its initial speed v is 1 mile per hour. Now according to Newton's law, this wagon is supposed to continue moving with that velocity 1 mile per hour in straight line forever. And this should be the case if there is no friction or air resistance. But in our world, we have friction and we have air resistance that cause an external force in the opposite direction. So we have friction, and this friction caused the object to come to a stop eventually. So this wagon will eventually come to a stop. The velocity will become 0 after moving a few meters. However, we still see many applications of Newton's first law. For example, when you are driving and you step on the brakes, let's say you're going with a speed of 50 miles per hour and you encounter a stop sign and you step on the brakes, what will happen to your body? Would it lean backward, forward, or would it stay still? From our daily experience, when we step on the brakes, we lean forward. This is actually because we are resisting the acceleration. And this is the essence of Newton's first law that was suggested first by Galileo, and he called it the law of inertia. Inertia means resistance. So basically what Galileo said, he said that objects tend to resist any change in their state of motion, meaning they tend to maintain their constant velocity. They want to move with a constant velocity. They tend to maintain the same speed and the same direction, meaning they want to maintain zero acceleration. And that's what Newton's first law states, that unless there is external force, and here we are talking about net external force, there is no acceleration. So in order to get acceleration, you have to apply force on an object. And if the net force is 0, then the acceleration is 0. What we mean by net force is the sum of the forces acting on the object, because sometimes you might have several forces acting on the object. Their net, the resultant force, is what we mean by net force. It's the total force acting on the object, counting the direction. So if you are driving your car at speed of 50 miles per hour going north, and you step on the brakes, bringing your car from 50 miles per hour to say 30 miles per hour, your body will tend to maintain its speed. So it's trying to maintain the 50 miles per hour velocity. And the only way to stop it is either by the friction between you and the seat, or by a seat belt, of course, which will be more efficient, or an airbag in the case of sudden deceleration, like going from 50 miles per hour to 0 velocity in a fraction of a second. In that case, the only way to stop your body from maintaining at 50 miles per hour speed is an airbag. By the same manner, we can talk about direction. You know, if you're driving your car and you are making a turn to the left, your body will tend to continue moving in a straight line. So you see yourself leaning to the right. And the same thing if you're trying to make a turn to the right, because your body is tending to maintain a straight line direction, you'll feel as if it's leaning to the other direction. So if you place a box on the top of your car and you make a turn to the left, you'll notice that the box will maintain straight line direction, falling on the right side of the car, and so on. So actually we see the application of Newton's first law in real life. And again, please watch that video in the notes for better in-depth insight. Okay, now let's look at Newton's second law. Newton's second law quantifies the first law. The first law tells you that there is no acceleration without a force, a net force, and if there is no net force, then the acceleration will be zero. Newton's second law quantifies the relation between the acceleration and the force, or I should say the net force. So the acceleration of an object is directly proportional to the force applied and inversely proportional to the mass. And those terms are very important to get familiar with. We'll be using them throughout the course, directly and inversely proportional. And we'll talk about what that means. So again, Newton's second law has two parts here. The acceleration is directly proportional to the force, and that's when you keep the mass constant. And usually we use this symbol for directly proportional, this symbol here. Acceleration is directly proportional to the force, F. And this is usually when the mass m is constant. We give the mass the symbol lowercase m. And the second part of Newton's second law tells us that the acceleration is inversely proportional to the mass. This is how we symbolize the inverse proportionality relationship. A, the acceleration is inversely proportional to the mass. And this is when the force is set constant. So what does that mean? That means if you have constant mass, like in this example here, you have this box, and you are applying force F to pull it. As a result, the box will accelerate with certain acceleration A that is directly proportional to the force. If you double your force by having a second person pulling the box along your side, then the acceleration will be doubled. So if you double the force, the acceleration will be doubled. And that's the meaning of directly proportional. It means if you increase one of them by a factor, the other will increase by the same factor. And here when we talk about factor, we are talking about multiplying it by a number. So if you double the force, the acceleration will be doubled. If you triple the force, the acceleration will be tripled. If you cut the force by 1/2, the acceleration will be cut by 1/2, and so on. So this is the meaning of directly proportional. Inversely proportional, on the other hand, means if you double one of them, the other will be cut by the inverse of the factor you increase the first one. For example, the mass and the acceleration are inversely proportional. So if you double the mass, acceleration will be cut by 1/2. If you triple the mass, the acceleration will be cut by 1/3, inversely proportional. So it's the inverse to whatever you do to the first variable. So whatever you multiply the first variable with, you have to divide the second variable by that number. So we can write an equation now to signify the relationship between acceleration, force, and mass. Acceleration is directly proportional to the force. Where should we place the force? In the numerator or denominator? Since the acceleration is directly proportional to the force, then the force should be in the numerator. And the mass has to be in the denominator, since mass and acceleration are inversely proportional. So this is one way to write Newton's second law. Acceleration is equal force over mass. Also we can write it as force equal mass times acceleration, or mass equal to force over acceleration. It depends on what you are given and what you are asked to find. And Newton's second law considered one of the most important laws, not only in mechanics, it's one of the most important laws in physics, where it quantified the relationship between acceleration, force, and mass. And mass is basically the inertia or the resistance that try to maintain the object motion. That's why a semi-truck is very hard to change its velocity than a light scooter, because a semi-truck has big mass, and hence to change its acceleration you have to apply big force. Now, very important part here is the unit. We learned before that the unit of acceleration is meter per second, and unit of mass is kilogram. Since force is mass times acceleration, as we learned, hence the unit of force will be unit of mass times unit of acceleration. So it will be kilogram times meter per second squared. And we call this unit Newton. So Newton basically is equivalent to the force needed to accelerate 1 kilogram of mass by 1 meter per second per second. And 1 Newton of weight is equivalent to 0.225 pound. So for example, if you are asked to find the force of gravity, and the force of gravity represents the weight of objects. There is difference between weight and mass, and this is important to distinguish between mass and weight. Mass is the amount of matter the object has, how much matter in an object. It does not change whether you are here on the Earth or on the surface of the Moon or on the surface of Jupiter, for example. While the weight changes. Why? Because the weight will depend on the acceleration due to gravity. Since force is mass times acceleration, as we learned, and since force of gravity has to do with the acceleration due to gravity, so the force due to gravity will be the mass times g, the acceleration due to gravity. So we can replace A here by g, which is 9.8 meters per second. So 1 kilogram of mass will weigh on the surface of the Earth 9.8 Newton. It's 1 kilogram times 9.8. While on the surface of the Moon, for example, the acceleration due to gravity is 1.63, if I recall correctly. So the weight of a 1 kilogram mass will be around 1.6 Newton. So hopefully it's clear now the difference between weight and mass. Mass is not a force, weight is a force. Weight is the force due to gravity. It's the force by which the Earth's gravity pulls you down, the force of attraction between you and the Earth. Okay, let's look at the second question here in the discussion. Here in question number 2, it tells you that a 10-gram bullet was propelled from the barrel of a rifle with a force of 3,500 Newton. What is the acceleration? So here you are asked to find the acceleration while given what? You are given the mass in grams, 10 grams, this is the mass, and you are given the force in Newton. And you are asked to find the acceleration. This is the unknown. This is what we are asked to find. We know the acceleration is force over mass, and the force is given to be 3,500 Newton, while the mass is 10 grams. Now we cannot do the calculation right now because the mass is given in grams rather than kilograms. Recall that Newton means what? Newton means kilogram meter per second square. So 3,500 Newton means 3,500 kilogram times meter over second square. If you divide it by 10 grams, kilogram will not cancel out. And here we need the answer in meter per second square, so the kilogram has to cancel out. So we have to convert 10 grams to kilograms. And to do that, we have to move the decimal point how many places? We have to move it 3 places to the left because kilo is 1,000. We learned in conversion that when we convert from small unit to a bigger unit, we have to move the decimal point to the left because we are increasing the unit, so the number has to decrease, and it will decrease by moving the decimal point to the left. Now how many places should we move it to the left? Since kilo is 1,000, which is 10 to the power 3, hence we have to move the decimal point 3 places to the left. So this will leave you with 0.01 kilogram. So we are dividing 3,500 kilogram meter per second square by 0.01 kilogram. Kilogram will cancel out. If you carry out the calculation, this will give you 350,000 meter per second or meter per second square. So this is how big the acceleration is. Notice that this is the acceleration, not the velocity. The velocity will depend on how long the acceleration was acting on the object. So 350,000 meter per second square is a huge number, and we expect this number because the mass is very small, meaning the inertia or the resistance is very small, while the force is big. Now Newton's third law is very important, and it has many applications. It states that whenever one body exerts a force on the second body in turn exerts an equal but oppositely directed force on the first. That is, force come in pairs, action, reaction pairs. And this is very important. You cannot find a single force. Forces always come in pairs. If you push against a wall, the wall will against you. If you kick a football or a soccer ball, it will kick you back. The harder you kick it, the harder it will kick you back. Now the question sometimes that might arise is, why we see different outcomes. Why when we kick a ball, for example, and kicking is the action, the reaction will be the ball kicking your foot back. Why do we have different outcome if the forces are equal, the forces of action and reaction? Why would the ball undergo very huge acceleration while your foot barely recoil, and sometimes actually the whole force will be absorbed within your tendons and flesh? And the answer has to do with this part of Newton's second law. Acceleration is inversely proportional to the mass when the force is constant. And here the force is constant. It's the action and reaction. And they are acting on two different objects. Action and reaction do not act on the same object, they act on different objects. When the mass is huge, the acceleration will be small. The bigger the mass, the smaller the acceleration. And vice versa. The smaller the mass, the bigger the acceleration, as we saw in the previous example with the bullet. So the ball has small mass, while your foot, which is connected to your whole body, has big mass. Your body has big mass. And hence, the acceleration will be smaller for bigger mass. So if you weigh 100 times more than the ball, then your acceleration will be 100 times less than the acceleration of the ball. And the same example can be applied on everything, like for example the kickback by a rifle when you fire it. The force on the bullet will be exactly equal to the recoil force by the rifle. But we know the acceleration will be different because the bullet has very small mass while the rifle has big mass. And we can see here several examples like launching a space shuttle. And this is one of the many misconceptions that some people have about how rockets accelerate upward. They think that the gases produced by the explosion of the fuel will push against the launching pad and that will cause the rocket to accelerate. And this is wrong because the rocket is still accelerating even in the space where there is no ground or launching pad. And the reason is action and reaction, very much like the case with the bullet. The explosion of the fuel will apply force on the fuel, causing it to accelerate downward. This is the action. The reaction will be the force by the gases exploded on the rocket directed in the opposite direction, which is upward. That's why the rocket will accelerate upward. And the same case here when you play tennis. Tennis racket will hit the tennis ball. That's the action. The reaction will be the tennis ball hitting back on the tennis racket. And as we said, the outcome is different because of the difference in the mass. The outcome always has to do with the mass, not the force. People confuse force and acceleration. For example, when there is head-on collision between two cars, let's say one of them is very small car, compact car, and the other one is a semi-truck, the head-on collision will apply the same force on both vehicles. So the force on the semi-truck will be exactly equal to the force on the small car. But the outcome is different because the semi-truck has big mass, hence it will undergo very small acceleration, and usually this acceleration will be absorbed within its frame, while the small car will undergo huge acceleration backward because it has small mass, and usually the frame of that car will not withstand such acceleration. So the cause of the damage is usually due to acceleration, not force. If the acceleration is small, no matter how much the force is, there will be no damage done. Like the case with airbags. The purpose of airbags is to decelerate you at slow rate. Instead of hitting the windshield or hitting the steering wheel, which will cause a huge amount of deceleration, you go suddenly from, let's say, 60 miles per hour to 0 in fraction of a second. Instead of that, you can go from 60 miles per hour to 0, but in several seconds. So this will make a huge difference. That will reduce the acceleration and hence the damage will be much less. I will go ahead and stop here. In lesson number 6, part 2, we'll talk about the gravitational force, the inverse square law, and the orbital motion. Thank you for watching this video. Please feel free to email me your questions.